Hello guys, and welcome to the second problem on mass spring damper system. So we are going to try to obtain the differential equation that relates the displacement x of t and x naught of t for the spring mass damper system shown below. Now we are given this particular spring mass damper system and we want to find the differential equation relating these two different displacements. So let's go. So as usual, the first thing to do is to define your reference direction. So defining our reference direction, so we are going to define our reference direction to be this way, okay, positive. So motions to this side is positive. So we are not really giving any input force, f of t, so to say. So perhaps I could just forge an input force by myself and f of t equal to 0. I could forge it by myself and assume that it's moving in this direction, or I could follow the direction of my displacement, and that will be my reference direction. So all motions in the reference direction are considered positive, while all opposing motions will be considered negative. Is that okay? So let's examine the free body diagram. So the next is the free body diagram. So the FBD. So drawing the FBD is very important in an exam scenario. You need to be able to draw the free body diagram because it's like contributing to your marks. Is that okay? So to draw the free body diagram, we are assuming that there is a force creating motion, which is a zero force. Let's say our f of t, which is actually 0. Now, also in this particular direction, you need to consider that your spring constant is also acting in front of the mass. So the spring constant through Hooke's law will contribute to the force. Now, normally, the spring constant or the force contribution from the spring constant is supposed to be kx. But you need to take note, or kx of t, you need to take note that there are two independent variables here, this and this. So if you assume that this one is in front of this one, okay, so you can't just say that the displacement is kx. You have to say k into x of t minus x naught of t. Is that okay? So that's how you actually say it. So instead of our origin to be 0, kx means that our origin is 0. But since you're dealing with two variables this time around, so kx minus kx naught, sorry, kx of t minus x naught of t means that I'm considering this as my new origin. You're considering the displacement between these 2 points. So the displacement between these 2 points will actually contribute to the extension that will contribute to the force that this particular spring will influence on this particular mass. So take note, anytime you have an arrangement like this, usually you take the difference between the one further ahead in your positive direction, minus the one behind in your positive direction. Okay, so k into x of t minus x naught of t. So that will be the second force contributing to motion in the positive direction. We have k into my x of t minus x naught of t, like this. So what are the forces that are affecting the mass? Of course, we have to take note of inertia. Okay, inertia is proportional, of course, to the acceleration, that's m d2. So this time around, we just have to play, since the motion of the mass is dependent on x naught of t, then inertia will be expressed in terms of x naught all over the t squared. Then finally, another force that is acting in the opposite direction is the damping force. So the damping force is also related to this variable x naught of t. Okay, it's not going to be x1 minus x, it's not going to be x minus x naught, because this x actually comes in at this position. So only this spring will evaluate the difference between this and this, but this one is going to take from this and the mass is going to take from this too. So the damping force is proportional to the velocity and this is the damping constant C dx naught by dt. So the velocity is going to be expressed in terms of x naught. Is that okay? So having gotten it like this, so you're now going to use the D'Alembert's principle. Okay, and the sum of all these forces, okay, all the forces in the positive direction, okay, minus the resisting forces, sorry, it's 2x naught all over dt squared minus c dx naught by dt. The sum of all the forces, or the algebraic sum of the forces, is equal to 0. So all we just needed to do was to rearrange this equation in this form. So solving it, we'll have our f of t, which is 0. So you have 0 plus, you have k x of t, then minus, you now have your x, sorry, you have k x naught of t, you now have minus m d2 x naught all over dt squared minus c dx naught over dt is equal to 0. So a good way to express your equation is output variable is equal to inputs. Okay, so the output variable will most likely be the variable associated with the mass of the system. The input variable is the one at the extreme edge, or the one close to the input force. So I'm going to put all the x naught terms to the right, to the left hand side, and take all the x terms to the right hand side. So if you rearrange this system, you're going to get m d2 x naught over dt squared, then plus c dx naught over dt, then you now have plus kx naught of t is going to be finally kx of t. So at this point, you can stop here. This is the differential equation relating the system. Okay, so the differential equation that relates this input variable to the output variable for the system. So I hope you understood it. If there's any question, leave it in the comment section. Please like this video and subscribe. In the next video, we're going to jump on some electrical systems and see how to resolve their differential equations and perhaps find their transfer functions. Thank you for watching, and stay blessed.